Welcome back to ElmerRacing. In this video we're looking into what makes Thor so good. Stay tuned. Quick recap for you guys. So our Thor engine is the back-to-back 2 times world championship winner, still undefeated, full billet circuit racing engine, and the first and so far only 4-valve full billet racing engine. And yeah, we do have another one also, a Rex, but that hasn't been in a race yet, so that one doesn't count. But Thor, so we recommend that for 1,500 horsepower circuit racing use currently, and so the long block weight for that is 106 kilos, and with a turbocharger, which we would recommend probably a GTX 5533R with the 88 millimeter inducer compressor wheel, and yeah, definitely running one of our cast turbine housings here to save a huge amount of weight off of that turbo. And with that sort of a setup, the sort of complete engine will be about 150 kilos, something like that. And that makes it the highest power to mass ratio OEM circuit racing engine ever made. Or I'm not sure if someone has made more engines, but like that has actually competed in races and actually like proven to work, so to say. So the previous record holder for that was the F1 V10 Honda engine, I believe. That was the last year of the V10 engines before they started going downhill with the technical regulations there. So specification wise, so our Thor engine runs a 94 millimeter stroke. We have a 116 millimeter bore. These are the pistons that go into that. So these are absolutely huge, larger than a factory big block Chevy, for instance. So really big. And yeah, this 116 millimeter bore goes together with a 122 millimeter bore spacing. So we have 6 millimeters of material left between the cylinders, and our current design is to run thin wall sleeves in that, and it's so this is really important to be able to keep the maximum possible amount of block material in between the cylinders, because that aids hugely with the block rigidity. So you don't want to like remove everything and put in these Siamese sleeves or whatever you would call them, where you like remove the complete inner section of the block, because your torsional rigidity like drops right through the floor, and that's not very good for a circuit racing engine where you have torsional loads and stuff like that. And also not good for normal running of the engine also, because that creates a torsional force also from the power production. So yeah, we want to keep the maximum amount of material there and run really thin as we dare, dry cylinder sleeves. And that's basically the sort of overall cylinder dimensions, and that brings us up to a little bit under 4,000 cc's. I think it was 3,900, about 80, something like that. So very close to a full 4-liter engine. So with the high rigidity, of course, I mean, you want to design it to be as rigid as possible, so you don't need to start adding material in really inefficient places. And this is one of the very important things for making a lightweight design. The circuit racing is not about making power. You need to make power, but you need to make that while keeping everything super lightweight. And that's where Thor fully shines, like the power to weight ratio. So designing the block, of course, that required some innovation on us on the CAD side on how to even be able to design that in a sort of efficient manner, to be able to still do some small updates and tweaks on that and get it very rigid. The cylinder head also, very lightweight. Crankshaft also very sort of how should I say, sort of fine-tuned and super honed design. So we showed this in a previous video, so you can jump back and watch that if you want. And really all the components, so the drysump suction pieces that are fully integrated into the design. So this also helps with weight and also oil control. So if you want to run a drysump system, then you want to have an engine that is fully designed to take advantage of that drysump system and not convert a wet sump engine over to a drysump system. Or you even see like some designs where you have a like scratch built engine that is designed to look like a converted wet sump system that has been converted to a drysump. Like, no, you want, if you're designing an engine to be a drysump engine, then you want to like incorporate that fully into the design. So as you saw in our previous video when we went through how the crankcase looks and things like that, so I'm not going to go into that in further detail. But yeah, incorporating that fully in the design to begin with helps save weight also. Now with a really lightweight design, I mean of course with really heavy designs also, but especially with really lightweight designs where you don't want any extra material anywhere, you have to take the component flex into consideration quite a lot. I mean, in some areas normally you don't really need to look into that too much, but especially when you're doing a really lightweight design, you have to like look at how much everything is moving around and flexing, because there's no such thing as you just make the wall thick enough and then it will be solid. And no, the reality doesn't work like that. See, like people quoting like how thick their like top surface on the engine block is or something like that, then yeah, that's kind of a face palm moment or something like that. That guarantees absolutely nothing. You need to really design things so that they flex sort of together, and in some cases even so with our Thor engine, for instance, the crankshaft rigidity is sort of taken a little bit into consideration in the sort of overall engine casing rigidity. So when you're pressing down on the piston, that wants to flex the crankshaft downwards and up, and flexes sort of the crankshaft, or like in a sort of banana shape or whatever you would call that. And if the engine casing is super rigid in relation to that, first of all, it's much easier to get binding in the bearings, so you need to run larger bearing clearances, which in itself isn't a problem, but it's also always a benefit if you can run smaller clearances. And the other thing with that is if you have a super rigid casing and a relatively flexible crankshaft, so in relation to each other, I mean of course they're always really stiff, but sort of in relation to each other, I mean they always flex a little bit. So if they flex sort of similar amounts, then you can distribute that sort of flex and get the bearing loading. So not only on the, so when you're pushing down on one piston here and sort of this way, and you have pistons on either side, you have the adjacent sort of crank bearings, the main bearings to like this piston section. Then when you're pressing down on that, you have the main loading is of course on the bearings closest to that. But if you have the stiffness tuned correctly, you can sort of distribute that a little bit so that you have some loading on the next bearing shells also. That makes the sort of whole engine move a little bit better. And this is something that we have taken into consideration also with this design. So it's, we've pushed it really far, and I mean we want to not just be capable of the power level that we quote or something like that, because we're building a clean sheet engine, or we were building a clean sheet engine. Now it's of course been tested and everything, but this is one of the differences also between OEM and tuned engine. So with the tuned engine you have ready components that you try to push the absolute maximum from, but with the OEM engine you need to design it so that you can meet your goal and hopefully have a little bit extra margin, so that if some components aren't absolutely correct, or something that you haven't built yet and can't test yet, like how that actually works, you need to have a little bit of extra margin there, which typically means that you can push the components actually much past what the sort of design target power is. And so this is like, the flex of things is something that is really difficult, or I think one of the most difficult things to do that is typically at university level mechanics and stuff like this is not really that sort of well gone through, but I mean there are good courses, and if you guys are going to universities or anything like that, then definitely look at the courses that go through flexible components, because when you start pushing components to their limit, then you have to take the flexibility into consideration, or you're losing significant performance benefits. Your components will be heavier, or you won't be able to get as much power out of them, or something like that. So flexibility is super important. Some people have asked if, why we don't have balance shafts, or like, but it's such a big engine, like without balance shaft is going to shake itself apart or something, and creating counter forces to the imbalance forces, so that reduces the amount of vibrations transferred to the rest of the car. And I mean, for racing cars that are reasonably well thought out, this is not a problem at all, especially for like a really well balanced engine like inline 4. But it's not always this clear. A really good example of problems with engine vibration levels, even in super modern times, so not like back in the day or anything like that. I mean, it's still an issue, like how much vibration can you tolerate. So the Porsche LMP1, this V4 engine that they ran in their 919 is super good example. So they first designed that engine because it's a V4 engine with, I believe, a 90-degree bank angle. When you have a V4 engine, so if you want to have an even fire, so for the intake manifold, for instance, and the exhaust manifold to work optimally, and that basically means that both of the pistons need to be at top dead center at the same time. So one is at the firing point and one is at the valve overlap point. But this creates a problem for a racing engine, because you want to share the crank pins on the crankshaft. So that would mean that you have, when one bank is at top dead center, the other bank is at 90 degrees. So that means you have a 90-degree offset between the banks. And if you have a 4-cylinder engine that is even fire, those firing intervals need to be 180 degrees apart. So that means you have an uneven firing engine, which then can create torsional vibration problems in the drivetrain, which was the issue with the Porsche LMP1 engine when they were developing that. Drivers were reportedly or allegedly complaining that the vibrations were so harsh that they had trouble breathing sitting in the car, and they had I believe gearbox or differential or something like that problems with the car also. So they had to go back and redesign the engine to make that engine even firing. And they lost some efficiency from the engine from that, but they had to do that to reduce the amount of vibrations. So it's not always a clear-cut case of how to do that and how much vibration can you tolerate. Now, driveline vibrations and engine vibrations, so these are kind of separate things. So the balance shafts basically, so if you have those take out sort of radial vibration from the overall engine package that gets transferred into the vehicle. And then these torsional vibrations that we just spoke about with the Porsche engine, for instance, on the drivetrain side, but those can also create big problems on the undriven side of the crankshaft, which you typically drive oil pumps from, and the camshafts either through chains or belts or something. And belts are, of course, much better because there's some flexibility and damping there, so they kind of act as a natural damper a little bit, which helps out hugely. But you see this problem on a lot of tuned engines, and it's so strange, like how people don't understand like what's happening. Like, you have an oil pump that works on a factory engine absolutely fine, but then on a tuned engine you start breaking the oil pumps, and it's like, yeah, well, you're putting out too much horsepower, so the oil pump isn't holding up. Like, why would there be more power being transmitted to the oil pump? Like, that makes no sense at all. Like, no sense. So what is actually happening there is, of course, people are either removing the vibration damper off the crankshaft, and so this type of vibration damper, so this is the example we use on our Thor engine. So this is a viscous type damper that we put on the front of the crankshaft. So this is not to reduce the radial vibrations from the engine, but this is to reduce the torsional, or is this rotational? I'm bad at English, oh man. But anyway, so this, when you have the crankshaft in this direction, so how this sort of rotational flex is, and that's what these dampers are for. So either in these tuned engines, people are either removing those dampers completely, and that's creating much more movement there in the free end, and that is yeah, those sort of higher load peaks are breaking the oil pumps, or you see people breaking the cam chains drives or something like that, especially with these two-step type, like these horrible ignition cut, rev limit, or launch control things that have no business in modern engines at all. But I mean, yeah, people want to run them, that's fine. But yeah, then you need to, like, it's not the oil pump's fault that it's breaking, it's being broken because you're increasing the loads for that. So yeah, instead of like doing upgraded high strength oil pumps, you should like fix the actual problem and yeah, run a vibration damper, either this viscous damper that, I mean, it has an optimum or a sort of a vibrational frequency that it damps, of course, but it has like no area where it worsens the vibrations in relation again to like typical OEM and some aftermarket dampers, where you have a basically a tuned mass damper type thing with either rubber O-rings or vulcanized rubber or something like that, and these are tuned to a specific RPM to dampen those the vibrations at that RPM, and this is a really efficient way to do that. But then at all other RPM, it's not as good. Of course, I mean, when you have rubber, that sort of flattens out, so you have a kind of a RPM window where it dampens. But then when you're at unsuitable areas in the RPM range, you end up having more vibrations than without the damper, and this is of course not ideal. I mean, you of course tune that to dampen the worst vibrations. So I mean, overall it's a benefit because it reduces the maximum torsional sort of loads on the components due to the vibrations. But a much better solution is to yeah, run this type of viscous damper, and this is also a much more durable unit that will hold up for higher temperatures, and you don't have the rubber degradation. And if you run a rubber type damper hard enough, then the rubber will just start disintegrating, and it's really difficult to notice you have any kind of problems. And this is also really good for triggering, because you can run triggering off the outside housing of this. That housing is directly coupled to the crankshaft without any kind of flex. So you may see some kind of OEM engines that have crankshaft trigger teeth on the outside of the damper with a vulcanized rubber in between and the crankshaft pulley. So you're basically measuring crankshaft RPM with some amount of flex between the crankshafts. So it's really bad. I mean, it's good for some OEM use, but yeah, not really good enough for racing purposes. So the cooling system side also needs to be looked into and designed properly. So you both need to have an adequate amount of cooling and get all the areas that need to be cooled the correct amount, and also you don't want to cool areas too much either. So it's kind of you really need to know what you're doing with the cooling system to get that designed. But you also want to have that so build in as much fault tolerance as possible into the cooling system, which we have done in our Thor engine again. So if there is some kind of leakage or something, so we designed the cooling system like from the engine component wise. Of course, I mean, the installation in the car is up to the team ultimately, but you want to design the cooling system so that if you have a leak, the last amounts of coolant are going to be in the engine. So if you have a leak, it starts like leaking out from the what is it, the not catch can, but like the overflow can or something like that starts emptying first, then the radiator starts emptying, and sort of as much of the hosing as possible, and then like the final water left in your cooling system is in the engine, so that you can run as far as possible with like a broken cooling system. You want to be able to use every last sort of drop of sort of potential to be able to finish that one last lap to just get over the finish line, or other types of scenarios. So there are multiple things to take into consideration with this. First, you need to have the water ducting through the engine in some kind of a smart way, so that you don't have like these recirculation things or like splitter things where you might end up sort of pooling the coolant in an area where it isn't going to be used if there's no circulation at all. And then you also have to design the cooling system so that you don't have any possibility of vapor pockets building. So any kind of vapor pockets or leakages through head gaskets for whatever 5 million different reasons, or low coolant system or something like that, so you have boiling or low coolant level, so that doesn't end up creating vapor pockets that block the coolant flow in some area, and that area then receives no cooling and ends up overheating horribly and just destroying everything. And this we've designed in our Thor engine and also our Rex engine, of course, to have direct channels from all areas through the cooling system out to the exit. So the exit water from the engine comes out at the highest point, and there is no sort of closed pocket where sort of vapor pockets could build. Everything flows out through there. So that is also something that really increases reliability and allows some kind of a small problem solving. So for instance, in 2018 at World Time Attack with the problems due to the incompatible head gasket with the engine, and that creating ending up in a result where you have some kind of small leakage there. The cooling system still worked absolutely fine, and there were no vapor locks in the system. And you always want to design things so that you're as fault tolerant as possible. So the coolant requirement in the overall engine, so that will depend on multiple factors. So overall rule of thumb is that the 100% of heat from the fuel that goes into the engine, you get 1/3 of that as engine power, 1/3 as heat in the cooling system, and 1/3 goes as heat out the exhaust system. But of course, this is not really like absolute reality, but sort of a really rough ballpark estimate that has been around forever, I guess. And it will get you in sort of general ballpark. But so when you start comparing different types of engines, one of the sort of actual physical measurements of how, for instance, the heat gets into the cooling system is what kind of surface area you have in your combustion chamber is one of the really important factors. And that will, so of course, depending on what kind of mean effective pressure you're running on your engine, you will need some kind of displacement for the engine. And that displacement then, depending on how many cylinders you split that into, will affect how much volume you have, or how much surface area in the cylinders you have per volume. So if you double the size of a cylinder, so volume-wise, it's not like a 1-to-1 ratio from the displacement in a cylinder to the surface area. So if you run a 1-liter cylinder or 2 half-liter cylinders, the 2 half-liter cylinders will have much more surface area than the single 1-liter cylinder. So for instance, running our 4-liter inline 4 Thor engine and comparing that to, say, a 4-liter V8 engine, we have much less surface area around the combustion chamber, so there's a much less heat loss into the cooling system, which allows you to run a smaller radiator, pack everything tighter, and of course has a sort of benefit also from the engine efficiency point of view, because your efficiency goes up. Not hugely, but it does go up, and that's, every kind of small gain is always a benefit that you want to have. Our Thor engine also takes full advantage of multi-axis billet design. So just don't want to just run components because they're billet. You want to run components that are actually better than what they otherwise would be. And to do that, of course, you want to take full advantage. So we want to run alloys that are as strong as possible. Again, keeping prices somewhat into consideration. So for instance, we run a alloy on all our billet engines that is about twice the strength of the 6061, 6082 or whatever. Those two alloys are really similar depending on if you're in the US or Europe. It's the other alloy, but they're like performance-wise extremely similar to each other. And we use an alloy that is very similar to 7075, which is about twice the strength of the 6062, or I'm not sure if I'm getting those numbers correct or not, but I mean, you will know what alloy that is anyway. I mean, you guys know all about these things, so yeah, of course. And yeah, so these types of really high strength alloys, they're not castable, because castable alloys need to have their viscosity optimized for the casting process. And these yeah, aluminum alloys are sort of finicky in that sense, that they don't really want to cooperate very well. So the high strength ones, especially the ones we're using, are not castable at all. So we want to take full advantage of that and use really strong alloys. It's more expensive, but it's also better. So yeah, we definitely want to do that. And also design wise, we want to take full advantage of that. So we want to design walls, so compared to casting components, for instance, we can run much thinner walls. And it's also we're not sort of geometrically constrained on what we can do. Of course, there are some types of pockets that you can't do with a billet design that you can do with a cast design, but sort of overall the benefit is so huge with doing billet design, if you design your component to take advantage of that billet design, that I mean, it far outweighs any kind of drawbacks that you have by not running a cast component. There was something else also. Oh yeah, something, of course, yeah, with yeah, especially with us trying to yeah, make things as efficiently as possible. So development and design time is extremely important for us. So compared to a cast component, for instance, I mean, you hear some people talk about, yeah, I mean, we can, like these days we can do a cast component so fast, like we can get a cast component in 2 months even, or like if we're really pushing it, like in 1 month. And like, dude, no, like we can design a component, do calculations on it, manufacture it, and get it finished machined in 1 month. Not just the casting process, but like do the whole thing in 1 month. Like you're like four doubling, is that a word? Maybe it is, who knows. But I mean, you're like really slowing down your development stuff if you're doing lots of cast components. So I mean, that's definitely not ideal. I mean, for series production, of course, that makes perfect sense, and it keeps your costs down, and if you're doing quantities large enough to justify the added design time and added expense of doing cast components, and the added weight, of course, also, because you can never get that designed as lightweight as a billet component due to the reasons I said previously. So yeah, but I mean, if it makes sense, then of course there's nothing wrong with a cast component. You can make cast components really fast. But yeah, we take full advantage of the billet system to make Thor really good. Now our Thor engine is really well designed. Yeah, 2 World Championship titles, undefeated so far. Absolutely fantastic engine. So where would we go with this design in the future? So we did look into, I mean, yeah, as we posted on our YouTube channel also, and I believe on our Facebook channel. So we were looking at doing a Thor X update for that, and we did some calculations for that, and yeah, I mean, we'll go through those here shortly. So we're looking at bumping displacement a little bit on the engine. I mean, yeah, we have some contacts and some further yeah, design options there to push the displacement up. We can probably go to 4.3, 4.4 liters, something like that. We could also, yeah, bump up our volumetric efficiency on the engine, and the RPM range, and the boost pressure also on the engine. I mean, yeah, now having test results from the circuit and knowing that, okay, I mean, like Thor engine, typical circuit racing uses nowhere close to even needing anti-lag system, so it would be very easy to be able to run higher boost pressures, which is always the trade-off. So if the more boost you need, the sort of higher the likelihood that you will need anti-lag or something like that to get the sort of off boost areas filled in with boost, basically. But yeah, if you're running low boost pressures, then that sort of level of power before boost and after boost is smaller. So then you have a, yeah, better solution and don't necessarily need as much anti-lag. But yeah, we looked into that, and yeah, I mean, we're showing some graphs for the estimated power outputs and stuff like that. But we were looking at probably being able to reduce the, I mean, again, at feasible sort of price levels, being able to reduce the overall engine package mass by maybe 10 kilos, something like that, might be possible to reduce that a little bit more, but yeah, that was the number we were going with. And yeah, bumping power levels up, and I mean, of course, running the new larger size turbochargers, probably maybe 5533 size, anything like that. So yeah, we have a turbine housing for that already that is really lightweight, and that is, I mean, absolutely mandatory to be able to run high power turbos while still keeping the weight down is our turbine housing basically. But that will only give us about a 2 times improvement in power to mass ratio, and that's not really enough for us. Now with 3D printing we could probably get that 2 times ratio even better, maybe 3 times, something like that. A little bit difficult to say because the sort of longevity of super lightweight 3D printed parts is kind of a question mark, so we need to do some testing on that to see how much they could actually be lightened. But the problem with those is that they get super expensive. When you start 3D printing large metal pieces, and I mean actual 3D metal printing, like not this sintering stuff, but actual 3D melting, so that you actually get a full consistent part that doesn't have any kind of like a 99.9% or anything like that, but like it's actually 100% metal, and you don't have all of these tiny small sort of trapped non-metal sections in there that reduces the fatigue resistance of that component. But anyway, so that technology is still really expensive, so we would end up creating a super expensive engine, which yeah would not be ideal. Again, I mean, we need to be able to keep the Thor engine, and I mean further developments of that. I mean, it's now super cheap and extremely price efficient, so we want to be able to maintain that, of course. Basically, going forward, we need a new engine design type completely, and we have looked into that, and yeah, we found some really how should I say, promising design types there that could have a much bigger than a 2-to-1 gain ratio from our current Thor engine, which is about 10 horsepower per kilogram ratio. So that's super interesting. We'll have to see how that goes in the future, of course. I mean, that's not something that we can put time and effort into now at all, but things to look forward to in the future, and maybe look at possible collaboration stuff, and recruiting opportunities and stuff like that to design and develop our things. But yeah, I mean, before that happens also, I mean, we need to figure out how to sell parts. I mean, we're really good at design and manufacturing and not so good at sales and marketing. So yeah, that's something we need to figure out how to do also. But I mean, it shouldn't be too difficult. We do have the world's best circuit racing engines, so that's not bad. That really brings us to the end of our Thor the story. We might next week, depending. So we have an interview recorded with Rod from the Rod from the RP968. We have an interview recorded with him, which unfortunately the audio is really horrible on. But I think the audio might be savable. If we're capable of saving that audio, then we might do a video for next week on why the RP968 is so good. And I mean, there's some really interesting stuff in there that you guys would probably be interested in seeing. But we'll have to see. If we can save that audio, then we will do that. If we can't, we'll see if that can be done sometime in the future or not. But if we can, that video will be coming out 10/7/2020, so July 10th. And for now, I'm Oscar from ElmerRacing, and this has been Thor the Story. And what was the heading of this? What makes Thor so good?